All right, hello again. I'm going to now go over my paper here about motion-based communication. So first of all, I'll cover what that is exactly. So essentially, it's conveying information with poses, gestures, trajectories, that sort of thing. Um, a lot of times it can include human agents in the loop or just the robots themselves. And it varies in scope. So we have a lot of times just showing intent, like signaling. Think of it like a blinker, right? Am I going left or right? Versus a language. And also it can vary with the equipment used. There's sometimes auxiliary hardware or perhaps just the agent. Now we'll talk about why. So essentially, it's a network-free alternative to communication. Um, This makes it immune to, electromagnetic interference or network attacks um, and disruptions. It can also serve as a common language channel for both robotic and human agents. So this is obviously useful in collaborative environments when you are working with multiple robots or people. So some of the limitations in the existing research, a lot of times there is a holistic mapping, essentially. And what I mean by that is you'll have a message such as follow me, and that'll be a certain sequence of motions, and it's not usually broken down into semantic symbols. So instead of we have a message go to location, we'll have to make an entirely new set of messages for go to and location because it's not broken down into these linguistic symbols. And a lot of times we have hardware constraints. So in this example, we see a wearable tech here that is used for dyadic uh, pose recognition, where the wearable technology will pick up a pointing gesture and go from there. So obviously that can cause a little bit of limitation in generality because we have to have the human wear that, and it can be more expensive. And then lastly, a lot of these the motion-based communication that actually use languages, they're kind of informally language-based, so that reduces some of the scalability. So the problem statement here is the modern approaches to this paradigm, they struggle with flexibility and generality, which can limit the scope of communication semantics and scalability. So the proposed solution here is to frame this paradigm as a pseudo-language and then implement a generalized model-free motion model or model-free motion framework, excuse me. Okay, so just an overview of the methodology here. I do a little bit of open coding. We perform open coding on robotic action literature to form an ontology. We encode this ontology using what we refer to as lexical motion units. We signal with a UR5E arm and then decode using optical flow and contour analysis. So the open encoding process just involves picking out relevant robotic literature and essentially coding these terms to get relevant robotic tasks. So what this allows us to do is form an ontology and priority of different messages that we may be able to send through this MBC method. So here is part of the ontology. It is organized into actions, action types, and then some atomic nodes to allow us to form sentences essentially. Okay, so the way the encoding works here is we can traverse this ontology and form a sentence, if you will. And so this here shows a brief example of the communication paradigm where we're going to have the arm move in a circular motion and initially start with a toggling gesture, which is that cross pattern. And then we go and send the sample messages. So each of these symbols essentially is a piece of a circular motion, and the oscillating motion is delineated by these shifts in direction. So I'll explain a little bit more about that later. But how we begin communication is we start with this TC signal, which I mentioned is a cross pattern. This helps to determine an ROI for the camera. And so what that does is it helps to mitigate noise and improve the performance of the subsequent decoding. And so right here, again, we have the UR5E doing that cross pattern, and the camera will establish this ROI zone here. Okay, so the decoding part essentially consists of optical flow, image pre-processing, and then some contour analysis on those optical flow vectors. And then we assign these to what I call optical flow contour or OFC objects. So let me just go briefly back and talk about what an actual like symbol is encoded as in this language. Essentially, the motion is consisting of like oscillating movements along a circle, and you can think of each segment of this circle divided into 15 degrees, which is my encoding angle that I picked. So 3 LVU or LMU would be equivalent to 45 degrees. And the arm can oscillate back and forth. And that consists of your signal. So the value for the LVU is calculated dynamically. And how that works is that when the TC signal is sent, we can basically approximate the value of that 15-degree LMU by using this radius. We take the magnitude of that radius, and we know the angle of the circle of that encoding angle, and so we can convert appropriately to get an estimation of that magnitude radius. So the way this was validated was 13 sample messages in that ontology from 1 to 5 meters. The evaluation was essentially how many of these shifts are correctly interpreted. So this table will show the number of shifts for each of these messages, and the accuracy from 1 to 3 and 1 to 5 meters. So between 1 to 3, we had a pretty high success rate, and then it falls off slightly, but still a reasonable performance. And the frame rate is pretty stable on a relatively strong processor. So the ROI does help a lot with that as well. When the robot is farther away from the camera, you can have better performance because the ROI will be smaller. So that definitely helps a lot as well. Conclusions here, the MBC can be framed as a language, which can help facilitate communication flexibility. This can be done without data-driven models, which removes model querying and other overhead. And the usage of motion primitives and no model can improve generality. With respect to other agents, this is just a quick example I showed of trying to communicate using just a random go with myself. And you can see we have 6 LMU for the two signals, and here it's 90 degrees and 90 degrees, and 6 times 15 is indeed 90 degrees. So it does indeed work pretty well with other non-robotic agents. So we want to test this more in resource-limited environments and dynamic environments, empirical evaluation with that human example, and extend the language. Thank you.